Section 12.1, Vector Valued Functions. I want to talk about vectors as they can be described as a part of some moving term along a particular circuit or path. The movement of such is said to have its magnitude determined by the function values. So here we have a vector R of t, and it has function components f of t and gt if we're in the plane, the xy space, or if we're in the three-dimensional space, the x, y, z space, then this particular path or position vector R of t has components f of t, g of t, and h of t. These are functions in respect to a vector. A vector is some quantity that has two things, direction and magnitude. And so if you're in the space, it's possible to have some vector R of t, which looks like the f of t I plus g of t j plus h of t k. The component here of I is a unit vector that runs with respect to the x-axis. J is a unit vector that runs with respect to the y-axis. And then K, a unit vector that runs with respect to the z-axis. Also, we want to talk as we go through this chapter about vectors, and you can calculate the limit of a vector, and we can also talk about the continuity. So the definition of the limit of a vector is tantamount to the definition for the limit of a function. To investigate the idea of the limit of the vector, it is tantamount to investigating the limits of the respective functions. So to evaluate the limit of RT as t approaches a, then that is the same as evaluating the components of the vector. The limit of f of t as t approaches a, and that is with respect to the emphasis from the x-axis. And then with the pole position of the y-axis, if we're in the plane, then you investigate what happens to f as t approaches a, what happens to g as t approaches a. Secondly, if we're in the space, the xyz plane, the limit of the vector is tantamount to the respective limits of the individual functions of f of t, g of t, and h of t. Likewise, we could talk about the continuity. The continuity of a vector value function is really understood in two pieces, if you will, that the limit of a function is said to be continuous if two things, that if the limit exists, the limit of R of t as t approaches a, that it actually exists. And then secondly, that if the limit of RT as t approaches a exists, here that limit ends up having a definite number and that this limit is equal to R of A. So two things even in the definition that you see is that the limit has to exist and that limit, what was that? Computer is crazy. That limit ends up being a definite point. You remember in calculus 1 that we said that the limit of a function exists as t approaches a if the left-sided limit is the same as the right-sided limit. That's for the plane for x, y. If it's x, y, and z, then you have several directions going on. So you have positions from x, y, and z, and then the combinations thereof. But it still boils down to the same, that the limit of the function R of t as t approaches a has to be some number for us to say that it's continuous. Excuse me. A vector value function R is continuous on an interval I when it is continuous everywhere, at every point on the interval.